First up, I'd like to introduce our speaker who's going to be with us today. We've got Tony Norton from Exeter Uni. He's the director of the Centre for Energy, Energy and the Environment. He's going to sort of, in a little way, go back maybe over some of the stuff that we touched on really briefly at the end of Sunday, but getting a bit more detail and a bit more, I suppose, focus now that you know it's going to be the topic that you're really going to be looking at. And really just remembering as we're listening to this, we're thinking about, you know, as part of the Devon Renewable Energy Strategy, what role should onshore wind play within the mix? Okay, so I'm going to hand over to Tony now and hope you enjoy the presentation.
Hello, good evening, everybody. I've been asked to cover a lot of material tonight, and I've broken it down into 3 bits. The first bit is going to cover energy and electricity. This will go over some of the ground that you've covered already, I believe. Then we're going to look at renewable energy technologies, electricity technologies, and then move on more specifically to onshore wind. The first bit's going to be in this first session, and then the last 2 are going to be in the second session. Now, I'm going to be presenting evidence, and there's quite a lot of facts to put over, but at the end of each of these sections, I'm going to produce a bullet point summary of what I think are the key points from the slides in that section. So I'm going to start off with talking about measuring energy, and of course, electricity in particular, to give a sense of perspective, really, and trying to start with something that I think we're probably all quite familiar with. Here we are, a low energy 5-watt LED light bulb. Now, these are things we all buy and put into our homes. So let's think about the implications of using that bulb. So if we run it for an hour, we use 5 watt hours. But of course, we run our light bulbs for more than an hour in the year. So let's say that we run it for 20% of the year. Now, I know that there are 8,760 hours in a year. So if I want to know how much energy in the year that 5-watt light bulb is using, and let's say it runs for 20% of the year, I multiply 5 by 20%, 0.2, times 8,760. Now, because 20% of 5 is 1, the answer I get here is that bulb running for 20% of the year, we use 8,760 watt hours. Now, there are 1,000 watt hours in a kilowatt hour. So that's 8.8 kilowatt hours a year. Now I can repeat that process for another household appliance, let's say a fan heater. Now this particular model is a 3 kilowatt fan heater. So that's 3,000 watts, which equals 3 kilowatts, it's the same thing. Now if I run that for an hour, that's 3 kilowatt hours. And let's say I run it for 15% of the year, just randomly, actually it's not randomly, I've chosen that number quite deliberately, because that gives me, when I multiply those numbers through, so 3 times 0.15 times 8,760, gives me 3,942 kilowatt hours. And because there are 1,000 kilowatt hours in a megawatt hour, it gives me 3.9 megawatt hours. Now that happens to be the average consumption of a UK household, the average electricity consumption of a UK household, interestingly. Now let's take a slightly bigger appliance. Well, not an appliance, but an electricity production device. A 3 megawatt wind turbine. So 3 megawatts is 3,000 kilowatts. And let's run that for an hour. It gives us 3 megawatt hours. I'm missing the H off that. That's a deliberate error. And I've run that for 28% of the year, which is about the average load factor for wind in the UK or wind in Devon. That gives me 3,359 megawatt hours a year. Now, because there's 1,000 megawatt hours in a gigawatt hour, that's 7.4 gigawatt hours. So lastly, let's think about 22 of those 3 megawatt wind turbines. That's the Fullerbrook Down wind farm in Devon. If those run for 28% of the year, which is the average load factor on wind in Devon, that gives us 162 gigawatt hours. And as there are 1,000 gigawatt hours in a terawatt hour, that's 0.2 terawatt hours. So there we have a sense of scale running through from a light bulb to a wind farm. Just looking at how that would compare, 3.9 megawatt hours is one home, 162 gigawatt hours is enough to power 41,000 homes. That's about 80% of the homes in Exeter. And that's a sense of scale that I think we need to appreciate when we talk about onshore wind. This is significant electricity production we're talking about. So that's my bit about measuring energy. Let's move on to talk about energy in Devon and where it comes from. So this pie chart here shows our current sources in 2018 of energy in Devon. 46% of it from petroleum products, 29% of it from gas, 20% of electricity, and the small 5% from coal and bioenergy. Now, the challenge we have is, of course, that even without electricity, about 76% of our energy is coming from fossil fuels. Now, we all know that that needs to change if we're to combat climate change. How's it going to change? Well, part of the answer is likely to be electric vehicles, replacing that petroleum that we fuel our vehicles with electricity. Part of it's likely to be changing the way I heat our homes from gas to using heat pumps, which also use electricity. So there's some big challenges about future energy use. What have we done over the past 10 years for our energy use? Well, that's 25 terawatt hours, the amount of energy we use in total. How's that divided up, and what have we used over the past 10 years is the subject of the next slide. So here are those different fuels with the figures from 2008 and the figures from 2018. And you can see that by and large, the reductions, and there have been reductions overall, about 5%, but they've been small, and that's over a 10-year period. How are they used? How is that energy used? Well, industrial and commercial, domestic and transport are all fairly evenly split. And again, you can see those small reductions coming through, 5% overall. The reductions in industrial, commercial and domestic are about 7%. The reduction in transport over 10 years is less. It's about 2%. So we've seen some small reductions. Now, when we look at the climate, why energy use is important is because it directly related in terms of fossil fuels to CO2 emissions. And the way we convert from energy use to CO2 emissions is by using an emissions factor. That factor is a simple multiplier that changes one from the units of energy to the units of carbon dioxide. Now, the factor for coal is high. The factor for oil is less high, but still quite high. The factor for gas is lower than for oil. Now, the reason I'm talking about this is because we've seen some big changes in the factors for electricity. And this has had some staggering results on carbon emissions so far. So let's look at CO2 emissions back in 2008. Here they are. CO2 emissions in Devon, 43% of them were from petroleum and other fuels, 19% from gas, and 38% from electricity. Total emissions were about 7,640,000 tons of CO2 equivalent. Now, if we look 10 years later, in 2018, that number had shrunk by 27%. Now, it's interesting that our energy consumption had shrunk 5%, but our carbon emissions had shrunk 27%. And you'll see a clue in these pie charts as to why and where that has happened. So in 2018, petroleum other products were 56%, gas 24%, but electricity 20%. So the proportion of electrical CO2 emissions have gone down from 38% to 20%. And the reason for that is because of the UK's production of renewable electricity. The Committee on Climate Change is, I guess, the go-to organisation for the journey towards net zero and producing evidence for it. And the next graph is a plot of theirs showing what has happened to the electricity emissions factor. Here it is. So back in 2010, the emissions factor of electricity was around 500. The black line shows what's happened since then. In 2020, it's now below 200. That is a remarkable drop. And there are two things mainly at play there. Firstly, in the UK, coal-fired generation has played a less and less a role in our electricity generation system. But of course, it's the penetration of renewables that has made the largest difference. Around half of our electricity now comes from renewable generation. The challenge is that you can see in the future, the Committee on Climate Change need to see our emissions factor for electricity going down further, to the point where by the mid-2030s, we've got virtually no carbon in our electricity. Now, when I talked about the pie charts earlier, we said that we needed to get rid of fossil fuels. So the petrol we put in our cars, the gas we use for our heating, that needs to change. And a lot of that change, the Committee on Climate Change's view, will come through electricity. And that has impacts on future electricity generation needs. And the next graph shows what the Committee on Climate Change believe we need to do with future electricity production. Here it is. So they see future electricity needs going up from around 300 terawatt hours, more than doubling to over 600 terawatt hours. You can see that the main uses are in residential buildings, so for heat. So that's the sort of orange and mustard color wedges at the bottom. And the other big wedge that's growing is the purple one, surface transport. This is electrification of our vehicles. So not only do we need to green our electricity, we also need to significantly double our electricity production. Now, the Committee on Climate Change also have a view about where that production is likely to come from, and that's on the next graph. We can see generation from fossil fuels in the electricity system falling off to zero by 2035. Variable renewables, which is the next wedge up, which include wind, become the predominant source of electricity generation. Some electricity is needed for hydrogen production, and there will be other sources of power, firm power, dispatchable low carbon generation that's needed to supplement the variable renewables that are in the big pinky wedge at the bottom. But there is no doubt that variable renewables like wind have a major role to play in the CCC's view about how our future low carbon generation evolves. So that's the first section of my talk. I've got a summary slide here to try and bring out the key points that I've been trying to make with all those graphs. And I do apologize for people who don't have graphs. This is a graph heavy presentation. So the key points: all sectors need to decarbonize. This means essentially doing away with fossil fuels that currently supply, well, 76 plus the half of electricity, 86% of our energy needs in Devon. Decarbonising electricity is essential because electricity is going to play a key role in decarbonising heat in buildings through the use of heat pumps and in transport through electric vehicles. And of course, developing any renewable electricity resources will help in this process. And that's essentially the first part of my presentation.
Okay, well, thank you very much.